Metals are everywhere in our daily lives. They form the skeletons of our cities, the wires that carry our voices and our energy supplies, and they're the tools that shape our world. We know them by their shine, their strength, and their ability to conduct heat and electricity. But what gives metals these remarkable properties? The answer lies deep within their structure. And it's a story that begins with the mysterious property that is metallic bonding. In the periodic table, metals dominate. Of the 118 known elements, nearly 80% of them are metals. They are defined by their willingness to give up their outermost electrons. And when many metal atoms come together, something extraordinary happens. Without a non-metal atom to accept an electron, what becomes of it? Well, those electrons begin to wander, drifting freely throughout the structure. We often describe this at GCSE as a sea of delocalised electrons. It's a simplification, but it's a useful one. In truth, while the reality involves overlapping energy levels and quantum mechanics, a topic for another day. For now, imagine a vast ocean of electrons flowing through a lattice of positive metal ions, holding the structure together. This simple model can explain much of what we observe in metals. Take malleability. That is the ability to hammer a lump of metal into a sheet. Within the metallic structure, the positive ions repel each other and yet are held in place by the surrounding sea of negatively charged electrons. It's a kind of mobile glue. And when you strike a piece of metal, the layers of ions can slide past each other without breaking that glue, and so the structure holds. It's this delicate balance of attraction and movement that allows metals to be shaped, and it's why we can put a dent in a piece of metal or forge it into a form. Stretch the metal instead of beating it, and those layers elongate, forming thin strands. This property is called ductility. That is the ability to be drawn out into a wire. Again, it's the freedom of electrons that makes this possible. Now, consider electrical conductivity. When a voltage is applied, the delocalised electrons drift from negative to positive, carrying charge throughout the entire structure. They can't escape, of course. They can only flow when given a complete circuit, and that flow is what we call an electric current. A similar story explains thermal conductivity. Normally, heat spreads through the vibrations of neighbouring atoms. But in metals, those mobile electrons carry energy far more efficiently, transferring heat across the whole material, from the pan on the stove to its contents, with ease. And what about that unmistakable metallic shine? When a surface is polished smooth, the uniform layers of atoms or ions reflect light in a neat and an ordered way, a specular reflection. That mobile electron glue makes it easy to produce a smooth surface, the one that is required to do this, and that's why silver, aluminium and steel can mirror the world around them. Now, we often describe metals as dense, hard and with high melting points, but that's not always the case. These properties depend on how tightly packed the ions are and how strongly the electrons bind them together. For instance, lithium, the least dense of metals, floats on water, and potassium is soft enough to be pressed out of shape with just a hand. Yet others, like tungsten, can withstand extreme temperatures without melting. These differences all stem from the same principle, that balance between the positive metal ions and their shared sea of mobile electrons. Finally, there's the sound of a metal, that clear, resonant ring. When struck, the ions move, but they can quickly spring back, and that movement can be transmitted through the whole structure. This results in a standing wave that travels through the metal and then out into the air as the sound we can hear. And that's why a bell rings or a cymbal sings. Every property, the shine, the strength, the conductivity of metals, can be traced back to that elegant relationship between the positive metal ions and that sea of free electrons. And it's astonishing to think that the world of metal, from the girders of a skyscraper to the circuits in your phone, owes its existence to forces acting on scales far too small to see. And this is the beauty of chemistry, the understanding of the invisible that leads to the explanation of the world we can touch. I'm the Helpful Chemist, and this is the story of metallic bonding.